Sir, in the lecture hall, no one is here.
Okay, that is fine. So I think many people may just log in, but you can keep it on at the lecture hall.
Okay, sir. But we are streaming here in the Emmy Noether.
Okay, okay.
Yes.
Yeah, actually for questions, it's easier if they log in directly because otherwise they have to come nearby and talk.
Okay.
Okay, I think I'll start. Are there questions from last time? Am I audible?
Yeah, yeah. Yes.
Okay. Okay, so if there are no questions, I'll begin. So last time we discussed how to deal with the singularities that come from the boundary of the moduli space. So last time. So today we are going to discuss, so these are the only singularities in bosonic string theory. But in superstrings and or in fermionic strings, let's say heterotic and superstrings, we have additional singularities which are called spurious poles. Okay, and here I'll give some example. Okay, the first kind of example is collision of PCOs. Say y alpha of, so we choose a section. Let me y alpha of u equal to y beta of u somewhere on SGMN. Okay, so let me remind you that SGMN is the section over which you integrate. Okay, and it's parameterized by the moduli space. Okay, and as you move in the moduli space, the PCO locations can change. Okay, and if they come on top of each other, okay, then there is a collision, and that produces singularity. Okay, because chi alpha, chi of w, chi of z, this is singular as w goes to z. Okay, and y alphas are basically the arguments of chi for the different PCOs. So this is one kind of singularity that one can get. The second kind is collision of PCOs with vertex operators. So this will take the form y alpha of u as pi of u, okay, where this is the location of the puncture. And if you want a specific coordinate system, you will call that around the puncture. Around each puncture, we use the W coordinate system. Maybe I label this by A because that's what we had called earlier. So around each puncture, you will use the coordinate system WA, and WA equal to 0 is the location of the puncture. Okay. So this basically means that y alpha measured in the WA coordinate system goes to 0 as you vary u. Okay, so this is another kind of singularity that you may encounter. And then there's a third kind of singularity. These comes on higher genus surface, not on the sphere. Where no operators collide. This, of course, doesn't happen in regular quantum conformal field theory, but it does happen for the beta gamma phi system. Okay. And essentially, you can trace this back, okay, to the fact, trace back to possible propagation of negative L0 states in the loops. Because as we discussed in the beta gamma phi system, on some vacuum, you can have arbitrarily large negative L0 eigenvalue. Now, we had said that this is not usually a problem because you can do analytic continuation. So recall that we had said that if you have a term like this, we declare this to be 1 over 1 minus x, even if x is greater than 1, right? When this sum doesn't converge. So x is like e to the minus L0. Okay? And if L0 is negative, or q to the L0, if L0 is negative, these things are larger than 1. Okay, and that's what is happening here. So even if x is larger than 1, we declare this to be 1 over 1 minus x. Okay. So this, of course, is possible, but this produces singularity exactly at x equal to 1. And this is what is responsible for additional spurious poles on higher genus surface. So today we are going to deal with this, okay, how to get rid of these additional spurious poles.
Ashok, you said that in the third type,
Yes.
there will be divergences where no operators collide, but in the modular space, there will be like infinite number of points where there will be no collision of operators, isn't it?
Yeah. So there are special points.
At special
not everywhere. Yeah. So this, maybe when I write, this will become clear. So these are not. It's not that There are divergences everywhere, right?
But special in what sense? Because we thought that boundary is special, and then this PCO and vertex operator collision points are special, and PCO and PCO collision points are special. Except
Yeah.
this, what other special points are there in the
Well,
model?
the other special points is that some function of z goes to 0.
Okay, okay.
Okay. That special points means, so special points take the form of some function of z goes to 0. Yeah, this is typically built from theta functions. The higher genus theta functions. So it's, but at z equal to 0, or at the 0 of f of z, there's no collision of operators. Okay, it's just some point in the moduli space where things blow up. Is this clear?
Yeah.
Right? Imagine that you are moving in the tau plane, and at tau equal to 2i, you get some divergence. But these, maybe I should say this, these also, that while these happen at points where no operator collides, okay, the positions depend on PCO locations. The positions depend on PCO and function locations. Okay, so I'll make it a little more detailed. So basically what it is saying is that the zeros occur at some function of the y alphas, then the zi's, these are the, or pi's, let me write these abstractly as pi's, pas, and u equal to 0. Okay, where these are the PCO locations. These are the function locations. And these are the moduli. Okay, and f is some known function. It's not, so in a given higher genus surface, there will be some function f that you know, and whose zeros will give you this spurious pole.
Sorry, Ashok, U is the moduli parameters or the full this fiber parameter?
No, u is moduli parameter.
Oh, just the MGN.
Yeah, just the MGMN, exactly. Because u I am using to label the section, right?
Yeah, but
See, the
earlier
section
you were
is labeled by the
writing
moduli parameter.
y alpha of U, and also I was confused as to what.
Oh, yeah, because on SGMN, see, this is not necessarily on SGMN. This is a general statement. Okay, so on SGMN, y alphas are functions of u. Right? Because if you recall the way we introduced, this is PGMN. Okay, these are the y alphas. This is the moduli. And this is a section. Okay. So a point here, right, is a function. So the y alpha, so once you have chosen a section, right, given a point in the moduli space, you go up, and that's y alpha of u. Is this clear?
Yeah. But I still don't get what form this singularity gets. Like functional form of the singularity is what? Like it's 1 over something, which is going to 0.
Yeah, it's 1 over something, exactly. There are some theta functions in the denominator whose vanishing points are the singularities. Yeah, so the theta functions
Meaning
depend on,
Heaviside functions.
no, not Heaviside, Jacobi theta, or the generalization of the Jacobi theta function on higher genus surface. So this is built from theta function on Riemann surfaces. Right? There are some standard functions. Okay, and so this f typically is built out of these theta functions and its derivatives. Is this clear?
So I mean, the claim is that besides the punctures, I mean, singularities coming due to punctures coming together, we can have such singularities which are due to analytic continuation.
Yeah, exactly.
Okay.
So what we are going to do today, is to deal all of this at the together, right? You don't have to give separate treatment for these kinds of singularities. Okay, and that will be based on one common property of all these singularities, which I'll try to explain now. So common property is that these appear on a codimension 2 subspace of MGMN of the section. Okay, so let me explain why codimension 2. So take the first kind, y alpha of u equal to y beta of u. Okay, two PCOs colliding. This is simple to understand. You can easily check that if you take two PCOs and take their OP, it diverges when the two arguments coincide. So this is a one complex equation which is equivalent to two real equations. So if you are using U to label the section SGMN, then you see, okay, we don't have to use U. You can use any other parameterization. Okay, it's either if it's a section, you can use the moduli coordinates. So if you choose to use U, okay, we can see that there are two real equations on U, okay, because they are given functions of U for a given choice of section. Okay, and that means that the singularity is codimension 2. Second kind, y alpha of U equal to PA of U. Okay. Again, one complex equation in two real variables. In one complex equation, so two real equations. Okay, so again, codimension 2. And the third kind, okay, that's the ones that appear on the higher genus surface. Okay, as I said, they take the form f of y alpha of u PA of u and u itself equal to 0. Okay. But f is one analytic function. Okay. So it's again a complex valued function. So you have to set both its real and imaginary part equal to 0. And hence it's again codimension 2. So one complex equation.
But didn't you a while ago said that this function and all is defined in the full fiber and not just the section?
Yes, it is.
So,
Yes, it is defined on the full fiber. Right? But I can choose to evaluate it on the section.
and it will still have roots.
It will still have.
It will still have roots on the section, this function f.
Yeah, so let me, so the codimension doesn't change generically, right? Let me try to explain this. Okay, so suppose, okay, let me, this will be needed anyway, so let me do this. Okay, so let's draw so let's pretend that the modular space is two-dimensional. Okay, because that's the best I can draw. Okay, so this is the MGMN, this is y alpha. Let's pretend that the fiber is one-dimensional. Okay, y alpha of course is complex, but let's imagine that it's taking value on a particular complex line. Okay, because again I cannot draw more than this, but this will be good enough for our purpose. Okay, so in this space, okay, the spurious pole location is codimension 2. Okay, which means it's a line. Is that clear? Now consider a section, okay, which will be two-dimensional in this case because MGMN is two-dimensional. Okay, so the section will be like this. And now you see that this line, okay, now let me try to draw this part a little better. Okay. So from the point of view of the section, okay, what we have, so these dots basically means part of it is below the section. Okay. So on this this codimension 2 subspace, this is a dimension 2 subspace, which is, sorry, not codimension 2, this is the section, okay, which is two-dimensional in this case. Okay, we see that it intersects this at a point. Okay, so even on this section there will be two equations that you have to solve, and it intersects at a point, and the problem comes basically from this point over here, right? So if you are trying to integrate over this section, this is our SGMN. Okay, then you hit this point and then you don't know how to integrate, okay, because this is where the integrand becomes singular. So it is true that, yes, go ahead.
Yeah, it may very well happen that this red line has no intersection at all with the section.
It may happen.
Oh,
It
and
may
then
happen,
don't worry about it.
exactly. Yeah. If it doesn't have any intersection, then you don't have to worry. But generically, it will have intersection, right?
I see, yeah.
Because a codimension 2 subspace, right, intersected with a dimension 2 subspace will have a point intersection.
Okay.
Okay, are there questions?
So I didn't understand this picture.
Sorry, I think there are two. Yeah, just go ahead one by one. Maybe
Go.
Ashik.
Go ahead, Ashik.
Yeah, no, I didn't understand this picture actually. So this is the bundle, and then the green thing is the section.
Yes.
Then what is this red line actually?
Oh, this is the spurious pole location. Spurious pole locus.
So it's a three-dimensional fiber bundle, and then codimension 2. It's a line. So
Yeah.
throughout this line, you will have spurious poles.
Exactly.
And then the statement is what actually?
Yeah. So then the section will typically intersect this spurious pole at a point. This spurious pole location.
Yeah.
Right. So this is codimension 2 also on the section.
Yeah, sure. Yeah.
So the point is, if you have a codimension 2 subspace of a bigger space, right? And now if you draw another subspace in that bigger space, on that subspace also, the intersection with the original codimension 2 subspace will be codimension 2.
Codimension. Oh, okay. Okay, sure.
They are putting two conditions, two equations.
Okay. And another question I had from beginning actually. So when you study this singularities coming from boundary, that you mean that HS plus HS bar going to 0. That singularity we discussed last time.
Yeah, exactly.
And there is no issue with two vertex operators coming close together.
Okay.
Nothing.
So I discussed not HS plus HS bar equal to 0, but HS plus HS bar less than 0, right? Because we discussed the generic case.
But then you said that is fine actually. That comes from some Schwinger parameterization kind of.
Exactly.
Yeah.
So that part you have already dealt with, right? So you are not going to discuss that anymore, except that in the special cases we have to do what know what to do. Yeah, that will require string field theory, which I might discuss later.
Yeah.
But generically, that singularity is gone because you can do analytic continuation.
Yeah, sure. But there was still that issue with HS plus HS bar equal to 0, even in string field theory.
Yeah, exactly. So that I'm not discussing right now.
Okay. And then in bosonic string theory, if you have two vertex operators coming close together, then there is no issue.
No, there is issue. That issue that we discussed last time. Right?
No.
When two vertex operators come close together, that is the kind of thing that we discussed last time.
Oh, yeah.
Right? So whether it's in bosonic string theory or in fermionic string theory, that problem is dealt with in the same way.
Okay, okay.
Why
That
This
what-
is other than that, you have all these spurious poles.
Exactly. So
Okay,
for
okay.
fermionic string, other than that, you have all these spurious poles, and that's what you have to deal with.
Yeah, okay, fine.
sorry, on this note only, the third kind of singularity that you're talking about, that on higher genus, some negative modes can cause some problem. Even
Yes.
the BC system has negative things, right?
Yeah, but it doesn't cause that problem.
That is a fact.
Yeah. So this is a special feature of the xi eta phi system, right? This, if you just had the beta gamma, there will be no spurious pole.
BC, you mean?
No, just beta gamma.
But
If you
beta
just
gamma is the xi eta phi, no?
yeah. But the point is xi eta phi has a little more information because you are also including delta beta and delta gamma,
Oh,
right? Because e to the plus minus phi, those cannot be written directly as local functions of beta and gamma, right?
yeah.
So this problem that this spurious pole location one can show is independent of the of the position of beta or gamma. Okay, so if the if you have a combination like del xi to the minus phi or eta e to the phi, then the spurious pole location doesn't depend on the argument of that combination.
But the way you earlier wrote it, that it is really like negative L0 states going in the loop or something like that.
Yes.
That artifact is just of the beta gamma system. I mean, the beta gamma system.
Yeah. The beta gamma system, that artifact depends on what picture number you are using.
Uh, okay.
Right? And basically the point is, I mean, because on a generic Riemann surface, right, you may choose to decompose in one way where you decide that, okay, you will only let the good picture numbers flow in that in various channels, right? But as you deform as you move in the moduli space, you are deforming the Riemann surface, right? Then another description may become more appropriate, right? If some other handle is becoming long, which you didn't include earlier in your description of what which picture number states flow, okay? Then in that handle, now a bad state could propagate, right? The negative L0 states.
This is not the degeneration part you're taking. You're saying it just
Yeah, not the
if
degeneration.
I'm not in picture number minus half or minus 3/2, but something else.
Yeah. So it's not from degeneration.
Yeah, okay.
Okay. It's not from degeneration, it's just that it blows up at a particular point. If we go back, right, this is, let me go back. Okay. So X is like Q. Right? Q equal to 0 is the degeneration point. Okay, that's not what I'm talking about. What I'm talking about is X equal to 1. Okay, those are the points where things blow up. So that's why they are regular points in the interior of the moduli space. Right? These divergences are somewhat fake. If you use the right picture number, you shouldn't get this. But somehow what happens is that as you move around in the moduli space, you get these divergences. Is this clear?
Yeah, I think
I mean, you can also do the calculus. I mean, write down the correlation function explicitly, and you find that these divergences are present. Right? The correlation function has these divergences. When you build the higher genus Riemann surface by the procedure that I described, okay, you will find that the correlation functions are have these divergences.
By higher genus, you mean, I don't know what exactly you mean.
Torus onwards. Torus onwards, you start having this spurious pole. This is the additional third type of spurious poles.
Okay, but it's not delta, beta, delta, gamma specific. Is it because of that? Like you are relating this to picture number, right? So is it? It's not there in bosonic.
It's not there in bosonic. No.
Okay. Okay.
Any other question? Okay. So basically, what we need to learn is how to integrate through this singularity. Okay. And this is done by a procedure which is called vertical integration, which I'll try to describe now. Okay. So the idea is the following. Okay. This is a surface. Okay. You first cut out a small region around the surface. Okay, this you will call D. Okay. This region need not be horizontal, right? Need not be parallel to this in the sense the different points on this we have different y alpha values, right? Because the surface itself may be slanted. Okay, it's not necessary that the surface is parallel. So y alpha can vary on SGMN. Then what to do is that you erect a cylinder on this. We call this C. And close it on top by a disk D. Okay, and you have to take the cylinder sufficiently high, okay, so that the spurious pole goes out of this interior, okay, through the cylinder. Okay. So C, okay, in fact, this is the main thing that you have to deal with. So C encounters the singularity. The singularity. Okay. But it has the feature, okay, that on C, okay, there is one coordinate, which is the vertical coordinate, okay, which as you change the vertical coordinate, only the PCO moves, the moduli don't move. Okay. That is different from what happened on S, right? If you go from one point to another, the moduli move. Right? That's why you could parameterize S by M, by the coordinates of M. Okay. On C, okay, there is one coordinate, okay, that when you vary that, only the y alpha changes, moduli don't change. Okay. The other coordinates on C will along the other direction, the moduli will change. Is this clear? Okay. So we can take, let me write it here, coordinate on C are T1. Okay. So only y alpha depends on this. And T prime, okay, which could be taken as moduli. As use, okay, except one. Because now, as far as this direction is concerned, the T prime basically labels the circumference direction, right? In this case, it looks like one dimensional, but that's because the cylinder itself is two dimensional. But in general, it will have one less dimension than what you had started with, than the dimension of SGMN, because one of the directions is then the vertical direction. Okay. So this is the reason why it's called vertical integration. That's what we are going to do is to integrate over SGMN minus D plus C plus, let's call this D prime. This D prime plus D prime. Okay. So instead of trying to integrate through this spurious singularity, we integrate by removing the disk, okay, then the cylinder, and then the top. Okay. And you can see that this is deformable to the original configuration, right? That is formally, this is deformable to the original configuration because you can just collapse the cylinder and make this into original configuration. Okay. So the formal proof that it doesn't depend on the choice of section still goes through, okay, except that you have to understand how to do this integral over the cylinder. Is this clear? Other questions?
This is in one direction. This T1, you are saying that cylinder C is like the vertical direction is T1.
T1, yes.
So in any direction, like because in like this Y alpha is represented by one direction, but
Yeah, in this case, I'm
actually,
assuming let's say only one PCO is there. Right? That
okay,
PCO will move.
okay,
Okay? But otherwise, I mean, if there are multiple PCOs, you have to take this vertical section, divide it up. Along each of these sections, only one PCO will move. Right? That will be the rule. But right now, let's suppose that you have only one Y alpha.
okay.
Okay, and that's how you are moving. Are there questions?
So what this is actually, so you hit the spurious pole in this fiber bundle in this section, then you avoid that point and go like vertically up, and there you do
Yeah,
your
see, you're not
integration.
avoiding that point really.
Uh,
Yeah, you avoid that point and go vertically up, but then you have to you do encounter that singularity on the vertical cylinder, right?
when you go up, you hit that. Yeah. You will. Oh,
Yeah. So you have to deal with this. Right? It's just that we encounter the singularity, we make sure that we encounter the singularity on the vertical direction.
so anyway, you will encounter singularity.
Yeah, anyway, you will encounter the singularity. So now I'll describe how to deal with this.
Okay. Okay.
By disk here, you don't really mean the two-dimensional surface, right? You need the full dimension of SGMN.
Yeah, exactly. It's just that I've drawn SGMN as a two-dimensional surface. That's why it's
Yeah,
I'm calling
and
it.
coordinates on C, T is not just one number, right? It's just some vector. I don't some two
Coordinates on D.
on C.
Yeah, C has T1 as one, right? And then the raised I call T prime,
Okay.
right? So the number of T prime is essentially the dimension of SGMN minus one or dimension of NGMN minus one. Because you see, C has the same dimension as SGMN, right?
Yeah.
Okay, because you have basically frozen the modular you have frozen on a codimension one subspace. You can see, right? This object is codimension one,
I see. Yeah.
at boundary of the disk.
And that is T prime.
That is T prime, exactly.
Okay.
And on top of that, on that you add T1. This picture should be clear, right? Because we are going to use this picture. So I'm going to draw it maybe again in the next slide.
But is the idea that like instead of so you skip integration over the base of the cylinder and you instead integrate over C and D prime?
Yes, that's right.
Okay. Because it is collapsible to the original base.
Yeah,
So
exactly.
this is equivalent.
Yeah. So this should be
Okay.
equivalent, except that you don't know. I mean, we'll define this as the integral that you will do because you don't know how to do this integral if you encounter the spurious poles in the horizontal.
Okay. Okay.
But I mean, further I have to explain why the vertical direction is easier.
Yeah.
So we have this C, right? That's what we have to integrate over. So this need not be horizontal. So let me draw it slanted. Okay, this can also be slanted. So our this direction is what I'm calling T prime, right? Which in this case is one dimensional, but in general it is multi-dimensional, one less than the dimension of MGMN. And this direction I'm calling T1. Okay. So below here, okay, on this curve, we have Y alpha of, let's call it Y alpha 1 of T prime. Okay. And on this curve, maybe I should use a different color here. And on this curve, we have some other function, Y alpha 2 of T1 prime. Okay, so the above and below are labeled by these curves are labeled by T1 prime, and on this y alpha can vary, right, which I'm calling y alpha 1, and on this y alpha can vary, that I'm calling y alpha 2. Okay, and T1 is the vertical direction. So now let's examine T1 dependence of the integral. Okay, I should have said that I can take this product over Bi that we had, right? Bi dti. In this case, it will be B1 dt1 with product over I Bi dti prime. Okay, so the pullback of the measure on this cylinder will be given by B1 dt1 times Bi dt prime I, because these are the variables that we are using, okay, to label the cylinder. So we'll examine the T1 dependence of the integral, right? Where does the T1 dependence comes from? So first, we have chi of y alpha T1. Okay. None of the other PCOs, if they are there, okay, depend on T1, because along T1, as I said, only one PCO moves. Okay, so in this vertical direction, even if there are multiple PCOs, only one moves. Okay, so none of the other PCOs depend on T1. Okay. BT1 does depend on T1, so BT1 is minus del xi y alpha of T1 but this is total derivative because y alpha only depends on T1. Okay. Now, so BT1 has this factor, del xi y alpha T1. Okay. Because BT1 has only this factor, okay, you see that there is the other terms on B, right, which involve the dependence on the transition function on T1. Okay. Those are simply not there because the transition functions depend only on the moduli parameters, right? They don't depend on T1. Okay, T1 is a direction along which only the PCO moves, nothing else depends on T1. Okay. So all those transition functions doesn't depend on T1. So these del Fs, del T1, these are all 0. Okay, so this is all the contribution to BT1. Okay. And once we have that this is all the contribution to BT1, okay, we see that BT prime I that, let me write it here, del xi, sorry, I mean here I should have written, in fact this was not correct, I'll correct it. See, y alpha can depend on T prime also, right?
Ashok,
Yes.
could you like y alpha 2 is the value of y alpha of T1 comma T prime at some specific value of T1, right?
Yeah, exactly. So T1 equal to 0 to 1, say.
I mean, there's no such thing as T1 prime that you have written in the brackets in red.
T1, yeah, exactly. No such thing as T1 prime.
No, which in above you have written something like T1 prime in the
No,
red.
T prime. This is this one?
No, in the red y alpha 2
Oh,
argument.
sorry. This is T prime. Is it okay?
Yeah, and
So
this first y alpha of T1 comma T prime kind of
Yeah,
thing.
yeah.
I mean, T prime is implicit maybe.
T1 comma T prime. Yeah, so I made it explicit now, right? That y alpha does depend on T prime, okay, but nothing else depends on T1. That's what we are going to use. That's why the T1 dependence doesn't appear from here, right? Other chi's have other y betas, right? They don't depend on T1. They can depend on T prime, of course. Okay. So the only other source that where T1 could have entered, okay, is that the other B's, right, could have involved, so other B's would have, and not could have, they do have, they have del xi y alpha T1 T prime del y alpha T1 T prime del T prime I, right? Other BIs, right, which are associated with the TI primes, will have terms like this. Is this clear? But now the point is that because we have picked the del xi already from BT1, right? BT1 only has del xi, this term. So you have to pick del xi from BT1. Once you have done that, then these terms cannot appear because these terms, the OP of del xi or del xi will give you 0. Okay, because they are Fermionic objects. Okay. And that's the sense in which other BIs, even though they could have had terms like this, okay, they actually do not depend on T1. Okay. And the positions of the punctures, of course, do not depend on T1. So BT1 also has, let me try to fit this in, minus 1 over chi of y alpha. Okay, I'm not writing the arguments, it's the same argument. Okay, that is the structure of BT1. Is this argument clear? So the main point is that the net factor, all the terms which can possibly have T1 dependence inside the correlation function are just 1 and 2. BIs don't have T1 dependence. They do have T1 dependence, but they don't contribute because the del xi with del xi will give you 0. And of course, the locations of the puncture, the vertex operators do not depend on T1. Right? They have no knowledge of what this T1 is. Is this clear?
Why was del fs by del t1 0? Because no other things are changing.
Yeah, because no other things are changing. As you are going vertically, right, you are at the fixed point in the moduli space. Right? You are not changing anything along this vertical direction.
I see. So the location of all punctures and all are just fixed.
They are all fixed.
And slightly naive question. The red line that you are drawing for the singular line, it cannot quite be vertical in any sense.
Well, the vertical means that it will not depend on y alpha, right? But as I said, PCO locations always depend on y alpha. The singularities always depend on y alpha.
I see.
So at least there will be one y alpha. Suppose the two PCOs are colliding, right?
Yeah.
There is at least one y alpha on which it will depend, right? The one which is colliding.
Yeah.
Just pick that one.
Okay.
So yeah, so that's important, that the line cannot be totally vertical because there has to be some y alpha on which it depends. Right? The spurious poles are dependent on the PCO location. Okay, so the strategy now will be that once you have identified the T1 dependence, we are going to carry out the T1 integral explicitly. So you'll be integral dt1. Let's take from 0 to 1. Okay, or bottom and top of the cylinder. 1 over chi y alpha T1 T prime minus del xi y alpha T1 T prime and then chi of y alpha t1 t prime. This is the explicit. This part is coming from, and this is the explicit PCO that you have inside. And so now you see that these cancel, and you are left with integral 0 to 1 dt1, the minus sign, del t1 of xi y alpha t1 is t1 prime. So this is t prime, not t. T1 prime, t prime. Which is essentially minus xi of y2 alpha t prime minus xi of y1 alpha t prime. Okay. Because if you recall the cylinder, if I draw the cylinder here, this was y1 of t prime, and this was y2 of t. Okay, so we have performed the integration over t, and you have expressed this as a difference between xi of y alpha 2 t on t prime minus xi of y alpha 1 t. Are there questions? So now you see what has happened is that the spurious pole has passed through. Okay. Now you have to do the integral over t prime on this line and on this line. Right? But those don't have any spurious pole, right? The spurious pole was it was going like this, and it was going like this, right? It has passed. So the vertical part of the cylinder, you have done the integral, okay? And because it's a total derivative, we have expressed the difference between two boundary terms, okay, which do not encounter spurious poles. And this, of course, relied on the specific form of the integration measure, the fact that B had this particular structure. Is this okay? Are there questions?
But this seems like it's leading to the correlation function having xi's.
Yeah, as if
Extra
so it's leading to correlation functions having xi's. So that sounds bad, but of course you can't. I mean, the correlation function involving xi's are known, right? So you can use them. Okay?
in this large Hilbert space.
In the large Hilbert space, right? Nevertheless, because you have the difference between two xi's, okay,
Oh,
it's
you can write
actually
it
in the
as
small
xi.
Hilbert, right? Because the xi naught goes away in this difference.
I see.
Okay. So let me explain physically also what's happening, right? What this means. Okay. So physically, what we are using write del xi of y dy. But this depends only on 1 and 2 and not on the path. Even if it passes through a singularity, passes through a spurious pole. Okay. So you have 2 points, 1 and 2, right? imagine that you have two curves, and there is a spurious singularity sitting somewhere in between. Okay. If it was just a current, right? Suppose it was just some dimension 1 operator. Okay. Then it could be that the integral over this minus integral over this is non-zero because there is a pole at this point. Okay, in fact we know that it's a singular point. Okay. But the fact that the xi correlation function exists, right, and the only singularities are poles, okay, means that the integral of this, okay, in fact doesn't depend on which contour you choose. In other words, the fact that it's a derivative of something means that the poles of del xi are always double poles. Okay, there is no single, the residue at this point is 0. Okay. That's basically what you are making use of. Is this clear?
But after doing the T1 integral, you have this. So one term is at the base, right? Again, this y1 of t prime.
Yeah, y1 of t prime, but those, but this is y1 of t prime is integrated over this surface, right? Over this
Oh,
line.
oh, so it won't hit the singularity.
You don't reach the singularity,
Okay.
right? So if I go back again, right, what I have done is that we have this integration over sgmn minus d, which was okay anyway. Okay? We
Yeah.
have integration over d prime is also okay. C was the problematic one. Okay? But now the integral over C I have expressed as a difference between an integral on top minus integral at the bottom.
Okay.
And along this curve.
Okay. Okay. So now there is no singularity hitting anywhere.
Now there is no singularity anywhere.
Okay. So this is why you want that line to exit at the curved surface of the
Exactly.
Yeah,
Exactly.
okay.
This is why you want the line to exit at the curved surface, because if it exists on a curved surface where only one y alpha is varying, right, and nothing else is varying, then you know how to do this integral.
Yeah.
Right, and express it as
Okay.
a difference between these two terms.
Yeah, okay.
What is this thing about the del psi will have 1 by, you are saying that del psi will always lead to 1 by z square terms,
Yes,
1
exactly.
by y square term.
Yeah, 1 by y square, and there will be no 1 over y term.
Okay.
See, if xi has a well-defined correlation function, then it's automatic, right?
Okay.
But suppose I had a logarithmic branch cut,
All right.
then del xi you can have a single pole, right?
Hmm.
So the fact that the xi correlation function doesn't have a log kind of branch cut, that's what you are making use of here. So even
But
though xi is not a part of, see, xi is not a part of the Hilbert space, right? So xi could have had bad singularities. Okay? But
oh,
the statement is that it doesn't have. Okay, and this follows from this formula that I mentioned by Verlinde and Verlinde, that they have an explicit formula for the xi eta phi correlation function, where the only singularities are poles.
oh, it's
And
not
that's
as
what
simple as that xi eta is 1 by z. The only non-trivial OP is that.
yeah, exactly. Xi eta has only, but see, spurious poles don't follow from OPE, right?
Yeah.
So the spurious poles could have had bad singularities for xi.
Okay.
Okay, but it doesn't. So that's the statement, that it doesn't have bad singularities for xi. Okay? It has poles, of course, but not logarithmic branch cuts.
Okay. Let me, like, you are saying that even in the terms of t, it doesn't have like non like other than something like simple pole, even in terms of t, like.
Even in terms of t, yes, because the point is, once it doesn't have for xi, del xi, right? It is, I mean, this argument is just, you are just changing variables, right?
Yeah.
Yeah. As long as it's del t of something, it's clear that it cannot have double single poles, right? because then it will be a del T of something which has a logarithmic singularity.
Yeah. Okay.
So then the general procedure, let me explain. Okay, the general procedure. There we divide the moduli space. Okay, so instead of trying to deal with all MGMN at one go, you just think of this as a collection of many small regions. Okay, and one convenient way to divide it is what is called dual triangulation. So triangulation basically means that you cover with triangles and tetrahedron and so on. Dual triangulation basically means that if you divide up the regions and take the dual, okay, then that becomes a triangulation. Okay, it's not very important, but it will be somewhat useful. Okay, and I'll illustrate this in this two-dimensional example. Okay. So dual triangulation, basically what it does in 2 dimensions, okay, and this can be generalized, is that it divides the moduli space into parts where the basic objects are not triangles. Parts are not triangles necessarily, not necessarily triangles. But the vertices are triangles. Vertices are trivalent. Okay, so you see here, every point, there's only 3 boundaries meet. Okay, that's the way. And its dual graph will be, sorry, this is not correct. This, let's remove. Okay, you divide them into small regions so that at every point only 3 lines meet, 3 boundaries meet. It's not necessary, but it just makes life a little easier. Okay, to do this. Okay. So once you have divided into the small chambers, okay, then we choose, let me call these chambers. Y alpha in each chamber avoiding spurious pole. And this can always be done because, I mean, as we discussed, the spurious pole location does depend on Y alpha, okay, the PCO location. So by once you have fixed a small chamber, you can just take the PCO locations in such that inside that chamber, there is no spurious pole. Okay, so there is a choice here, there is a choice here, there is a choice here, and so on. Okay, so let's call this choice, say suppose it's here, it's Y1 alpha, here it's Y2 alpha, Y3 alpha, and so on. Okay, and then you define the integration method, okay, by in the usual way on each chamber separately. But this means that on the boundary you have to add some correction, right? Because y's are not necessarily continuous on the boundary. So what to do on the boundary is that on the boundary you erect a vertical direction. Okay, so let me explain this in the next page. Okay, so now I'm going to draw this as 1-dimensional, okay, even though the actual thing is 2-dimensional. So imagine that you have, this is one chamber, this is another chamber. Okay. So chamber 1, This is chamber 2.
Are you saying these chambers are defined after vertical integration or something?
No. So vertical integration, let's leave aside for now. Okay, I'm going to describe how it comes in. Okay, so vertical integration, I described how to avoid the spurious singularity, right?
Yeah.
That was an isolated case. Okay, and now I'm going to give a general procedure by which you can avoid all spurious singularities.
Okay. But these chambers are defined on the section, right?
These chambers are defined on the moduli space,
Oh, not on the.
not
But,
on the section.
but why are they not continuous?
In the moduli space in the moduli space they are continuous. Now what I'm going to describe here, this picture is, this is our choice of Y alpha, and this is MGML. Okay. Now I'm going to erect on each chamber a segment of a section.
I see. Not a smooth section, but
Pardon?
you are not putting a smooth section, but on each chamber specifically, you are erecting different Y alphas.
Exactly. On each chamber, I'm erecting different sections. Okay. Whatever you want, but making sure that it avoids the spurious singularities. Is that clear?
Yeah.
Okay. So on each chamber, let me write it again. So on each chamber, we erect separate independent sections. Independent section segments. Let me call it section segments because the base itself is not the whole moduli space, right? Avoiding spurious pole. Okay. So here is a chamber. I've drawn it as one dimensional, but in general, it's of course the dimension of MGMN, right? That's what it is. Okay. Similarly, this is also dimension of MGMN. At the boundary, boundary is codimension 1. The Y alphas don't match. Okay, so here it's Y alpha, sorry, Y alpha corresponding to section 1, and here it's Y alpha corresponding to section 2. This part you connect by the vertical integration. This we use vertical segment. And so carry out the integration like this, right? Which basically means that on this part, we put this del xi Y alpha. This kind of integral. Okay, which is precisely what we got here. These integrals. Okay. So the choice of section, just like here you erected a vertical cylinder, right? Here what I'm saying is that instead of waiting for where the spurious pole is coming, right, we just erect vertical segments whenever at the junction of two chambers. Okay. Some of these may encounter spurious pole, some of these may not. Okay. But if it encounters spurious pole, you know that it doesn't affect the integral because the final integral is only a difference between the top and the bottom. Is this point clear?
So none of these chambers hit any singularity. Now it's.
Yeah, none of these chambers hit any singularity because you have chosen it that way.
Oh, okay.
But there may be some spurious poles which pass through the vertical segments because spurious poles are there, right?
Yeah.
They may be moving
And
like this. Spurious pole location may be moving like this.
it
Right?
may or may not be there for a
May
vertical.
or may not be there, right? But whichever spurious poles are there are some spurious poles somewhere, right?
Yeah.
But they are chosen so that these sections are chosen to avoid those spurious poles.
Yeah, okay.
Okay.
And
So that
why can you do this actually? Like like changing the integration from one section to like suddenly and at one part you are going to some other section. This is because of that section independence. No.
No, the reason that you cannot do this usually, but here we are doing it because we are actually connecting them.
And let's say in that initial picture you draw of you ignore the base of the cylinder and instead you did it over D prime and C.
Exactly.
And is it obvious that that is fine? Like instead of doing it over.
Well, I mean, it's a question of what you mean by that is fine. That gives a finite answer.
Is that the same as doing it over the base? You
We
can't
don't
do it
know
over.
what the integration over base is, right?
Oh, but
Then there should be some proof, right? The integral over the base should
isn't
be
it
same as.
Stokes' theorem that will allow you to claim this?
Yeah, it's Stokes' theorem applied to singular integrals, right? Which can sometimes break down. Right? So what I'm saying is that this is the way you define this integral, right?
Oh, okay.
It's like as if you are applying Stokes' theorem. Okay, because in Stokes' theorem you can certainly deform the surface, right?
Yeah.
But the catch is that this integral was singular, right?
Yeah.
So use this as a definition of what this integral is.
Okay.
So that's basically the point.
But the fact that it does not depend how high in D prime, like D prime where you place exactly and all, is Stokes' theorem, right?
Yeah, exactly. The physical amplitudes, I mean, it's basically Stokes' theorem in the sense that this is what we describe, the section independence. We gave a proof of section independence, right? For the physical amplitudes.
Yeah.
The same proof will go through here. That because we say that if there are two sections whose boundaries coincide, where there is no boundary contribution, then they give the same integral, right? And that will be here, true, right? If suppose you erect it a little higher. Right? This part of the integral will give the same result as on the D, right? If you integrate over the cylinder or cylinder plus the top or just this one, it's the same result. Right? And that is the result of the application of Stokes' theorem. Is this point clear?
Then no, I can just use then section independence to argue that it should be same as C plus D prime, right? Integrating over the base.
Yeah, except that here you are applying this theorem on a singular integrand.
Oh, okay.
Right? That's why it's not, I mean, because this part is not quite well defined, right? Otherwise, you are right that if you didn't have this singular integral, right? If there's no spurious pole, then it's clear that whether you integrate over the SGMN or this part, right? SGMN minus D plus C plus D prime, you'll get the same answer.
Yeah, sure, yeah.
So it's the question of when there is a singularity, then this is the only way to get the answer.
Yeah, okay.
Okay, so it should be clear that this procedure that I'm describing here is just a special case of that, right? On each of these, this is like a vertical cylinder. Okay. So if it encounters a spurious pole, it's not a problem because the result of this vertical integral is written as the difference between the contribution from here and the contribution from here. So let me state this again.
Okay, one question about it. I mean, if I take the simple example of torus with the fundamental domain of tau, where will I encounter the spurious? It's along the center, the imaginary axis.
No, its spurious poles depend on the location of the vertex operators, right?
Okay, so I cannot just consider that. Okay.
Yeah,
I'll have to
imagine that you are a torus with various vertex operators, right?
Yeah.
Then this has how many dimensional moduli space? This has a the tau and the Z1, Z2, Z3, right? One you can fix.
Yeah.
So these are the 8-dimensional moduli space. And the spurious poles will be codimension 2. That means there will be 6-dimensional surfaces inside this 8-dimensional moduli space.
Okay. 6-dimensional surfaces.
Yeah, because codimension 2, right?
Yeah. Okay.
So there will be in general some 6-dimensional subspaces inside this 8-dimensional moduli space.
Okay. I mean, what I was thinking of is like trying to relate it to the fact that at q equal 1, I will encounter. I mean, that's what you said in the example, right?
Yeah. But the point is that those definitions of Q, right, are that once you have a complicated Riemann surface, right, then the Q's, I mean, which surfaces, maybe I can say it this way, that imagine that you have a complicated Riemann surface, right? Then there are many ways to think of this as made of handles, right? The A and B cycle decomposition, right? You can make it the standard one that you can see here, right? This, and then for this and that. But there are many other ways to do this. Right?
Okay.
Suppose you make one decomposition and you say that okay, only the good states flow along this channel, right? But then as you deform the moduli, right, then some other cycle may be getting stretched and the bad states may start flowing along that cycle.
Okay.
And that's where does these singularities come from.
Okay.
Okay, so along the vertical direction, let me say again. So along the vertical direction, we have integral, or maybe not even integral, psi of y alpha 2 okay, so one with a minus sign. So the idea is that in this, if you look at this picture, right, along this direction, right, there is one less integral along the moduli space, right? There will be, of course, I mean, here I have drawn it as one dimensional, but this vertical, the vertical slice will have one T1. One is the analog of T1 that we had earlier, right? That integral will give you xi of minus of xi of y2 alpha minus xi of y1 alpha. But there are, of course, other directions that you have to integrate over, right? Those have the standard measure in using those BIs. But by expressing it this way, you ensure that the spurious poles don't affect these definitions, right? These integrals are free from spurious poles, and these are, of course, finite because they don't encounter any spurious poles by choice. What time is it? I'm trying to check. Just 1 minute. I think I can try to finish this today. So let's draw this chamber picture again. We have this, say, 1, 2, 3. Okay. So as you jump here, you get xi of y2 y2 minus xi of y1. Okay. Then across this jump, here you get xi of y3 minus xi of y2. And around 3 and 1, you get xi of y1 minus I of y2, y3. So for single PCO, if we have a single PCO, then we can just stop here. Which means nothing further has to be done. But if you have more than one PCO, okay, then there are additional things that needs to be done, right? And that's what I'll try to explain now. Suppose you have two PCOs. So in this case, again, let me draw this. 1, 2, 3. Here you have y1, 1, y1, 2. Here you have y2, 1, y2, 2. And here you have y3, 1, y3, 2. So now, when you go from 1 to 2, right, that vertical segment, we have to divide into two segments, one along which the first one moves, the second one along which the second one moves. So suppose, let's take a prescription. Suppose at 1, 2 boundary, the vertical segment is y1, 1, y1, 2. These are the two PCOs. Okay. You first move it to y2, 1, y1, 2, and then you move it to y2, 1, y2, 2. Okay, so along each of these, you can apply the formula that I wrote out earlier, right? Because only one PCO is moving at one go. So between this and this, okay, we'll have a difference between the size, and between this and this, you have a difference between the second size. Is this clear?
Along the
So,
vertical direction.
yes.
So now it should be that both y1 and y2 should change, right?
Yeah, both y1 and y2 should change. But if you want to make the vertical integration that I described, you have to
Then
change.
you're doing it in two steps.
Yeah,
Oh.
you have to do it in two steps.
Oh, first
You could
only
reverse the
y2
step.
fixed.
Yeah, that you could reverse the step, but in any segment you have to move. You can move only one.
Okay, okay,
Try to
fine.
move
Yeah.
two together, then again the result becomes ambiguous, right? Then the this trick doesn't work quite well.
Yeah, sure. Yeah, this is fine.
Yeah, so you move one at a time. Okay. Suppose you do the same thing here and same thing here. Okay. So I'm going to draw a picture. Okay. So the picture that you will draw is something like this. This is y1, this is y2. So the first movement is like this. So this is 1, this is 2. Okay, this is chamber 1, this is chamber 2. So we move y1 first, then y2. Is this clear? That's the way you go from chamber 1 to chamber 2. Then, say, when you go from chamber 2 to chamber 3, suppose you move again y1 first and y2. This is chamber 3. Let me call it C1, C2, and C3 so that it's this is C2 to C3. And then at the last step, when you go from 3 to 1, right, again, suppose you move Y1 first. And then Y2. And now you see that there seems to be a problem because these don't quite give a, these don't collide. This is a non-trivial region, right, that you have left out. Okay, so let's contrast this with the case when we had only one PCO, right? In the case of one PCO, you first move from 1 to 2, C1 to C2, then from C2 to C3, and then C3 back to C1. So there you have basically retraced the path, but here you are not retracing the path, right? There's an area that is left over. So it turns out that in this case, what you have to do is that we take, so this is a codimension 2 subspace of the moduli space, right? So let me write, this is codimension 2. This point is codimension 2. So in this case, you have to compensate, okay? Just like here, we had compensated for the jump in the Y's, right? Here, you have to compensate for the fact that the path that you have followed from 1 to 2, 2 to 3 does not quite match up with the path that you have followed from 3 to 1. Okay? So you have to compensate by doing an integral over this area. And that integral, we can calculate what it should be, right? And that turns out to be integral del xi y1 del xi y2 del y1 del y1 del t1 del y2 del t2 dt1 with dt2. Okay, maybe I'll write it in the next slide again. Okay. So we have this area left over, right? So correspondingly, we have to add integral over this area. Okay, let me write y1 of t1 t prime. Let me write y1 of t1 t2 t prime. Because y's can depend on everything. So this is the compensating term that you have to add. Okay? And then, of course, you have to integrate it over this codimension 2 subspace. Okay? And then integrate it over the t primes, which is now codimension 2. Is this clear? So this is this is what you have to do to compensate for the fact that this curve is not trivial, right? There is an area that you have enclosed, right? so that when you go from 1 to 2 and 2 to 3, 1 to 2 and 2 to 3, and then back to 3 to 1, okay, you have not quite retraced your path, but you have come by a different route. Okay, and that's why on this, so this is the total dimension always remains the same, right? This is codimension 2 on which you are doing a 2-dimensional integral. Okay. Now it turns out that this is again a total derivative. You can easily check. Okay. So this can be expressed in terms of the corner points. This is can be written in terms of corner points. Right? Which means basically that if you have a spurious singularity somewhere in the middle, it makes no difference, right? Or even a spurious singularity that crosses this line, that it makes no difference. As long as the corners are chosen to be free from spurious singularities, you are fine. Okay. And now the point is, for 2 PCOs, you can stop here. So for 2 PCOs, you can stop here. We can stop. But if you have higher number of PCOs, say 3 PCOs, you have to go one more step. Okay? Because now these rectangles, okay, you have to now check if these rectangles enclose a non-trivial cube, right? And if it does, then you have to integrate over that cube. Okay? And the integration measure will again be like this, del xi, del xi, del xi, right? A 3-dimensional integral. Okay? And that again can be expressed in terms of the corner points. Okay? So this is the way we can get an unambiguous result out of this vertical integration procedure.
This rectangle, this 2-dimensional area, this is supposed to be the contribution from the point in between, you were saying. The point.
No. This is supposed to be, this can be expressed in terms of these points.
Okay.
Right? So the result of this integral can be expressed in terms of these points.
No, that's all right. But this is supposed to represent the contribution, somehow contribution coming from the 4-dimension 2 point between the 3 chambers.
Exactly. So at this point, right? So the point is just like on this, there is a jump, and hence you have to add a vertical segment, right?
Yeah.
Similarly, here at this point, there is this jump. Okay? And for this, you have to add this integral.
But
At
a
this
jump
point, there is
across
jump.
each lines, we have to add 2 vertical segments, right? Like y1 1 has to go to y1 2, and y2
Yeah.
1 has to go.
It's 2 vertical segment, but that is just a curve, right? Like
Okay.
this. Like this. This is the vertical. I'm calling this whole thing as a vertical segment, right? But you are right, this is 2 vertical segments. Here y1 is moving, here y2 is moving. But it's still a curve. It still has topologically a line, right? It is also a line. It is also a line, but the enclosed surface is this is a surface, okay? And effectively you integrate over the surface of this del xi wedge del xi. Okay. That's what you have to erect over this. And as I said, if now there are 3 PCOs, then when the codimension 3 boundaries, right? When these codimension 2 boundaries now intersect at a codimension 3 boundary, right? On that you may have a cube left over, right? And then you have to integrate over that cube.
Okay.
So this is the general procedure that you have to follow to define the superstring amplitude, which does not suffer from the spurious poles. Okay, so I think that's the end of the lecture. Any question?
Yeah, that first picture we drew, if you think of it in terms of this chamber kind of thing, there it was 2 chambers, right? One at the base and one with like cylindrical kind of thing.
Exactly.
There was some jump from 1 to 2, and then we come back from 2 to 1, and there we added only one.
Yeah. So let me explain the chamber language in that there, right? They are the 2 chambers where So 2 chambers, one of them was SGMN minus D, that is the chamber below. Okay. And the
Yeah.
other one was D prime.
Yeah.
Okay. And this is a vertical segment that connects the two.
Yeah.
Right. So this is the picture that I'm generalizing now. Right. Here we are, if there's a single PCU and a single locus of spurious singularities, then it's enough to just divide it into 2 chambers, right? And just make sure that the first chamber doesn't have spurious singularity, second chamber doesn't have, and then the vertical segment is what intersects the spurious singularity. But in general, there are many you can divide it into many chambers, right? There are many spurious pole locus, and so I mean the most systematic way is to just make them into small chambers, make sure that inside each chamber there's a spurious pole, and then you erect a vertical chamber, the vertical segments, right, which intersect the spurious poles. So
Yeah,
what I
but
This
guess,
is not a triangulation, right? I mean, this is not triangulation that you drew there. I mean, it's the
yeah, so triangulation actually is not necessary.
yeah. This is like just you moduli space. You draw one line, co-dimension one line, and
Exactly.
you
Yeah,
just divide it into 2 parts.
exactly. Yeah.
Okay.
I just drew a codimension one line and divided it into 2 parts, right? And that was enough.
But here it was looking good actually, because here you just have to integrate, skip the base and integrate over C and D prime. In the general case, when we are doing the same procedure, somehow you have to by hand add an extra thing due to the fact that this curve has a non-trivial area.
No, see here also, suppose there is another spurious pole location, right?
Yeah,
Then you have to again divide this out,
yeah.
right? So now you'll have 3 chambers instead of 2,
Yeah.
right?
Now, what does that area you added will look like here? Is it easy to see?
Oh, here. No, here, because in this picture, I have only drawn
One
one
TCM.
boundary, right? Okay. See, these boundaries could intersect. If they are in a complicated system, right? There will be another boundary that is needed between this and this boundary need not, could intersect another boundary.
That is where this corner contribution comes.
Exactly.
You're saying.
Exactly.
Oh, okay.
Right. So what we are saying here is that if you have, let me go ahead. That a general picture will be that you have a surface, right? This is the section, and there are many spurious. There are many places where the spurious singulars may intersect, right? In general, there are many, right? And then you have to cut out regions around each of them.
Yeah.
Right? These are the points where the spurious pole locus is intersecting. Okay, you have to cut out regions from each of them, and they could intersect.
Okay.
So you cut out like this. Right, and those boundaries themselves could intersect, right?
Yeah. Yes. Yeah.
So that's what I described in general.
Okay.
That if you have many spurious singularities, then you have to divide into small chambers and make sure that inside each chamber there is no spurious singularity, and then you connect them. Right?
Okay.
In general, it is not necessary. I mean, in any given problem, right, the number of chambers that you need is finite. It's not necessary that you have to triangulate and you have to make small chambers.
Okay.
But
Okay.
the description in using small chambers is the most general one. That you just make them small enough so that there's no spurious pole. And that you can always do, doesn't matter how many spurious poles there are. And then you compensate by using these vertical segments.
Yeah. Okay.
So here in this picture, it's like, I mean, instead of integration over this, you integrate over disks, right? You go up from this. Suppose this is the horizontal direction, and I go out of the plane, okay, to erect my sections, right? You just erect sections in various places at various heights, and then you draw the vertical segments to connect them.
And only issue is that like if there is a corner, like intersection point, then you have to instead you have to take contribution from the corner also.
Exactly.
That is this new area thing.
Exactly.
Okay. Okay.
And this problem will come only when there are more than one PCOs. As
Yeah.
I said, if there's one PCO, then it doesn't matter because you are moving it like this and then like this and then coming
And
back.
you're
Right?
just yeah, sure.
So then you don't have any gap left over.
Yeah.
But if you are moving two PCOs like this and then this, right? Then this question of gap left over comes in, and you have to make you have to compensate by adding additional terms.
Yeah. Okay.
So from the, if you think of the, if you ignore the spurious poles, right, and just look at what it means in the on PGMN, right? What you are trying to do is you are drawing a continuous segment in PGMN over which you can integrate, right? And that continuous segment involves some vertical segments. Okay? And the point is, it's not enough to draw just the vertical segment for on codimension one subspace of the moduli space. You also need vertical segments on codimension 2 and codimension 3 subspace of the moduli space.
Oh,
Right,
that's why it looks like this corner. It's yeah.
Exactly. So the surface is always the total dimension remains the same, right? Because on codimension 2, you erect a dimension 2 object, right? 2 surface.
Yeah.
So in PGMN, it will actually look like a continuous surface.
Yeah.
Okay? That's important because it has to look like a continuous surface so that you can apply Stokes theorem.
Yeah.
Okay? So it's just that if you don't include this additional piece, if you don't include this piece, then it will look like on PGMN, you have drawn a surface which has a hole left over.
Oh,
and
okay.
then you cannot apply Stokes theorem anymore.
Okay. Oh,
Is this clear? So the main point is that if you view it as a surface in PGMN, you should have no hole left over in the surface. And in the cases that we described where these things, when there are two PCOs that move like 1 to 2 to that first one, then 2, and then again first one, then 2, and first one, then 2, then there'll be a hole left over in the surface unless you fill this.
This is like in the one PCO case, like if you don't have that curved thing, then in the PGMN it looks like there is a hole. That was
Exactly. Exactly.
Yeah.
Right?
Okay.
This is just a generalization of that. In the two
Yeah.
PCO, even if you fill it, you will find that there is a hole left over unless you fill it.
Okay. Okay.
Any other question? Okay, so then I think I'll
No,
stop
no,
here.
I had one more question actually.
Okay, yeah.
From the beginning actually, from last class, like when you taught this boundaries of this basically these degenerations, that looks like points are coming close. Let's say last class you described where I guess Z1 comes close to Z2 and on. There also like points are coming close together, but still to get a singularity, you have to have one more condition, right? This HS plus HS bar going to 0.
Yes, that's right.
What does this mean actually? So points just coming close together is not enough.
Meaning you can, you see, the integrand has a singularity. Is that you can treat it by analytic continuation. Okay. If you have integral dq, q to the minus alpha, right?
Yeah,
minus,
yeah.
then this is singular for for alpha less than 1, right? For alpha greater than 0.
Yeah, this we do, but the alpha going to 0 was an issue, right?
Yeah,
True
exactly.
issue from
Yeah. Alpha
and
going to
he
0 is a genuine issue, right? And as I said, that has to be dealt with using string field theory.
oh
But for general amplitudes, this issue doesn't arise. For example, take a tree level 4-point amplitude, right? Say take tree level even n-point amplitude. Let's take 4-point, right? there what happens is that if you take 4 points, right? And if 2 of the points come close together, okay, the
Yeah.
momentum that is flowing through is K1 plus K2.
Yeah.
Right? And this gives a contribution to L0, which is alpha prime over 4 K1 plus K2.
Yeah, plus K2.
So for generic K1 plus K2, this is not an integer.
Yeah.
So you cannot cancel it by some the integer that comes from the oscillators.
Yeah.
Right? So then it's perfectly fine. You can define it this the way we defined last time.
Yeah.
Right? It's only when you are on a pole, right,
Uh,
that the problem appears. Right? And that in string theory, even in quantum field theory, right? Suppose you're calculating an amplitude like this. Okay? And you have Q1 plus K2 square. So this is 1 and 2. Plus m square equal to 0 for some massive particle.
yeah.
Right? Then this is a problem in quantum field theory also, right? Because this will go on shell. This propagator is K1 plus K2 square plus m square inverse.
Then there you do this resummation kind of business, right?
Well, I mean, yeah, the way you have to do the resummation, that's a more tricky here, right? Because this is tree level. There is no resummation involved here.
Yo. Oh, yeah. Yeah.
Okay? But the point is that, I mean, if this process is possible, then what one can show is that this pole, after you take into account the quantum corrections, it develops an imaginary part.
Okay.
Okay, because it's an unstable particle. If it can be produced in the collision of two particles, the reverse process means that this particle can decay into two particles, right?
Yeah.
It's an the particle which propagates in this channel is an unstable particle. Okay? So its renormalized propagator will have an imaginary part.
Oh, okay.
Okay? And that's what makes this finite.
Oh, okay. Okay.
But that requires the full-fledged field theoretic analysis, right? You cannot do it at the Feynman diagram level.
Yeah.
So that's the reason why these kinds of problems, right, they do appear in string theory. They better appear because string theory is supposed to be describing quantum field theory in an appropriate limit, right?
Yeah.
But they have to be dealt with using a field theoretic method and not the standard quadratic method.
Okay. Yeah, sure.
So that's the physics that this 1 over h plus h bar that we got, right? When h plus h bar is 0, there is a genuine problem. But those problems really have to require the field theoretic understanding.
Okay.
Any other question? Okay, so if not, we'll stop.